From space, Earth looks calm because the danger is invisible. Blue magnetic field lines rise from the planet, curve into space, and fold back around it like a glowing shield. Then a storm of solar particles slams into that shield from one side. The lines bend backward. The front of the shield compresses. The far side stretches into a long magnetic tail, as if the Sunday is pushing on Earth with a wind you cannot see. Nothing on the ground looks different at first. The oceans do not boil. The continents do not crack. Cities do not burst into flame. A person standing under a blue sky would not feel the magnetic field wrapping the planet, and would not feel the solar wind pressing against it. But above that sky, something is always happening. Space is not empty. The Sunday is constantly throwing charged particles outward, and Earth is constantly standing inside that stream. The magnetic field is one of the reasons space does not simply arrive at the top of the atmosphere unfiltered. Now let the glowing lines weaken, not vanish in one dramatic second, not collapse like a movie shield, just fade, soften, and lose their grip. The solar particles that once bent around Earth begin pressing closer. More energy reaches the upper atmosphere. The auroras expand. Satellites move through harsher conditions. The invisible boundary between Earth and space becomes less protective. The question is not whether Earth would explode. It would not. The real question is more unsettling. If the magnetic field were gone for long enough, what would happen to the atmosphere, the technology around the planet, and the living world beneath a weaker shield? To answer that, the story has to begin far below the clouds, far below the crust, beneath the mantle, in a place no camera can fly. Deep inside Earth, metal is moving. The outer core is not solid rock. It is a vast layer of molten iron and nickel, under enormous pressure. Moving around the solid inner core, heat escapes from the deep interior. The planet rotates. Hot material rises. Cooler material sinks. The flow is not smooth like water in a bowl. It twists, folds, churns, and organizes itself under the rotation of the planet. That motion matters because moving electrically conducting metal can generate magnetic fields. Earth's magnetic field is not a decorative aura added around the planet. It is the visible result, if we could see it, of a deep planetary engine. Scientists call this engine the geodynamo. The word sounds technical, but the basic idea is physical. Moving conductive fluid inside the planet helps maintain a magnetic field that reaches far into space. The field does not come from a giant bar magnet hidden under the crust. It comes from a planet that is still internally alive. Picture the outer core as a dark ocean of metal. Bright currents rise in slow columns. Sheets of molten iron twist under Earth's rotation. Where the motion becomes organized enough, magnetic structure emerges. The field extends outward through rock, ocean, atmosphere, and finally into space, where it forms a huge region called the magnetosphere. The magnetosphere is not a hard shell. It is a moving, breathing magnetic environment. On the side facing the Sunday, it is compressed by solar wind. On the night side, it stretches far away from Earth into a long magnetotail. It changes with solar storms. It pulses, it reconnects. It lets some particles in and keeps many others moving around the planet. The shield is real, but it is not perfect. That imperfection is why auroras exist. When charged particles from the Sunday interact with Earth's magnetic environment, some are guided along magnetic field lines toward the polar regions. They collide with gases high in the atmosphere. Oxygen and nitrogen release light. Green curtains ripple, red glows shimmer higher up. Purple edges flicker like electric silk. Auroras are beautiful because energy from space has entered the atmosphere. They are not signs that the shield failed completely. They are signs that Earth's magnetic field is directing and shaping the incoming energy. The same system that protects the planet also creates one of the most dramatic displays in the sky. Now imagine that system much weaker. The auroral zones could shift and expand. Regions that rarely see auroras might see them more often during strong solar activity. The upper atmosphere would receive more charged particles. Space weather would become more important, not just as a polar spectacle, but as a broader condition surrounding the planet. But this still is not the same as the surface becoming instantly deadly. Earth has another shield, the atmosphere. The atmosphere is thick compared with the fragile skin of magnetic protection in space. It absorbs many forms of radiation, scatters particles, and protects life on the ground from much of the harsh environment above. Even if the magnetic field weakened significantly, the atmosphere would still matter. It would still block a great deal. People would not suddenly need spacesuits on the sidewalk. The danger works across layers and time scales. Some effects would be immediate for technology. Some would be stronger during solar storms. Some would unfold slowly over thousands, millions, or even billions of years. That difference is the key to understanding the real answer. Start with orbit. A satellite circles Earth above the thickest protection of the atmosphere. Its metal body, solar panels, sensors, memory systems, and communication equipment are exposed to the space environment. Satellites already have to survive charged particles, radiation belts, solar storms, and changing conditions in the upper atmosphere. Engineers design for this. Operators monitor space weather. Satellites can enter safe modes when storms become dangerous. With a much weaker magnetic field, that environment becomes harsher. Charged particles can damage electronics. They can interfere with sensors. They can build up electric charge on spacecraft surfaces. They can degrade solar panels over time. High-energy particles can flip bits in memory, disturb instruments, and shorten mission lifetimes. A satellite that normally passes through manageable conditions might spend more time in regions where energetic particles are a serious problem. The first civilization, level consequences would not look like fire from the sky. They would look like signals failing, navigation systems becoming less reliable during storms, communication links degrading, satellites needing more shielding, more careful operations, more replacements, astronauts facing greater radiation risks beyond the densest protection of the atmosphere, airlines and communication systems becoming more sensitive to extreme space weather events, especially at high latitudes. Modern society is not protected only by the atmosphere. It is also protected by thousands of machines operating in the region where the magnetic field matters most. Now look at the radiation belts. Earth's magnetic field traps charged particles in enormous regions around the planet known as the Van Allen belts. This may sound like a danger, and for spacecraft it can be, but the belts are also part of the larger magnetic architecture that shapes where particles go. The system is not simply magnetic field. Good, radiation gone. It is more complicated. The field traps, guides, redirects, and sometimes accelerates particles. If Earth had no significant magnetic field, the structure of those belts would change dramatically. There would be less magnetic trapping in the same form. More solar particles could interact directly with the upper atmosphere. Spacecraft would face a different and potentially more punishing environment. The boundary between the solar wind and the upper atmosphere would move closer. The planet would not become an exposed rock in a single day, but its relationship with the Sunday would be rewritten. The next scene happens above the atmosphere, where the solar wind arrives. The Sunday does not just shine, it blows. A constant stream of charged particles flows outward through the solar system. Most days, this wind is steady enough to be background weather. But during solar storms, especially when the Sunday releases powerful eruptions, Earth can be hit by dense, fast, moving clouds of magnetized plasma. When those clouds reach us, the magnetosphere can shake, field lines compress. Energy enters the system. Electric currents intensify high above the planet and sometimes induce currents in long conductors on the ground. Power grids, pipelines, radio systems, satellites, and navigation can all be affected by severe geomagnetic storms. This can happen even with the magnetic field present. The field does not eliminate space weather, it shapes it. A weaker field could make some of those problems worse. More energy might reach lower magnetic latitudes, more regions might be affected. Satellite operations could become more difficult. The upper atmosphere could heat and expand more during storms, increasing drag on low Earth. Orbit satellites. Orbits could decay faster. Space debris tracking could become more complicated after major events. Again, the planet is not exploding, but the systems around it become more vulnerable. The shield is invisible, so losing strength in that shield is not cinematic in the simplest way. The lights stay on until a storm arrives. Satellites keep working until particle exposure damages them. The sky stays blue while the upper atmosphere changes. The danger is not a monster at the horizon. It is a new background condition for every machine that depends on predictable space around Earth. Then there is the atmosphere itself. This is where the story slows down because atmospheric loss is not usually a one-day disaster. Planets lose atmosphere through several processes. Some gases escape because they are light and fast. Some can be stripped more easily when the upper atmosphere is heated. Some loss is driven by interactions with solar wind and ultraviolet radiation. Some depends on gravity, chemistry, temperature, volcanic activity, and replenishment from below. A magnetic field helps, but it is not the only thing keeping air on a planet. Venus has no Earth, like global magnetic field, yet it has an extremely thick atmosphere. Mars has no strong global magnetic field today and has a very thin atmosphere. The difference is not just magnetism, planet size, gravity, atmospheric chemistry, distance from the sun, geological history, and solar activity all matter. That is why the careful answer is not no magnetic field equals no atmosphere immediately. The careful answer is, without a strong global magnetic shield, Earth's upper atmosphere would be more exposed to direct solar-wind interaction, and over very long periods, that could make atmospheric loss more significant than it is today. To see why this matters, look at Mars. Look at Mars. Mars once had a thicker atmosphere and liquid water on its surface in its early history. Today it is cold, dry, and thin. Its global magnetic field disappeared billions of years ago, though crustal magnetic patches remain. Without a strong global magnetosphere, the solar wind can interact more directly with the Martian upper atmosphere. Spacecraft have observed atmospheric escape from Mars into space. Mars is not Earth's exact future, it is smaller, its gravity is weaker, its internal engine cooled differently. Its atmosphere was more vulnerable for multiple reasons. But Mars is a warning image. A planet can lose habitability over deep time. When its atmosphere and magnetic protection change, no return to Earth. Earth is larger than Mars. Its gravity is stronger, its atmosphere is denser, its interior is still generating a field. Its climate system, oceans, chemistry, and geology are different. If the magnetic field weakened, the most dramatic long-term atmospheric changes would not happen instantly. They would build across vast timescales, especially under the influence of solar radiation and solar wind. This is why the timescale matters more than the fear. Day without a magnetic field is not the same as a million years without one. A temporary weakening is not the same as permanent disappearance. A magnetic pole reversal is not the same as losing the whole field forever. That last point is one of the biggest misunderstandings. Earth's magnetic poles move. The magnetic North Pole is not fixed in one place. Over geological history, Earth's magnetic field has reversed many times, meaning magnetic north and south have switched during a reversal. The field can become more complex and weaker than usual for a period of time. But a reversal does not mean the field simply goes to zero and leaves Earth naked to space. The geological record contains many reversals, and life continued through them. That does not make reversals meaningless. They are scientifically important. They may involve weaker field strength and more complex magnetic structure. They could affect radiation exposure in space and perhaps expand auroral regions, but they are not the same as a sudden total disappearance of Earth's magnetic field. So when someone asks what would happen if Earth lost its magnetic field, the first correction is this. We should not confuse three different scenarios. A normal pole reversal, a weakened magnetic field, a true long-term loss of the geodynamo. These are different stories. A pole reversal is part of Earth's natural magnetic history. A weakening field can increase exposure and space weather vulnerability. A permanent loss of the geodynamo would be a much deeper planetary change, implying that the core motion maintaining the field had failed or changed so much that the global field could not be sustained. That would not be just a sky problem. It would be a sign that something profound had changed inside Earth. The geodynamo depends on heat flow, core composition, rotation, and convection. Earth's magnetic field has changed strength and direction throughout geological time. It is dynamic because the core is dynamic. But for Earth to truly lose the magnetic field permanently, the interior engine would need to stop maintaining a strong global field. That is not expected to happen suddenly tomorrow. The core is not a switch someone can turn off. To imagine the consequences, we need to separate the realistic from the cinematic. Cinematic version: the shield disappears, solar radiation floods the surface, life ends quickly. Scientific version: the magnetic boundary weakens or disappears, the upper atmosphere and near-Earth space become more exposed. Satellites and space systems face greater particle hazards. Auroras and radiation environments change. Over long time scales, atmospheric escape may increase. The surface remains protected by atmosphere and ozone from many hazards, but the planet's long-term relationship with the Sun becomes less forgiving. The ozone layer matters here too. Magnetic field does not block ultraviolet light from the Sun. The atmosphere, especially ozone, plays a major role in absorbing harmful ultraviolet radiation. If the magnetic field weakens, charged particle precipitation can influence upper atmospheric chemistry, and energetic events can affect ozone chemistry in complex ways. But it is not correct to say the magnetic field alone is what stops sunlight from sterilizing the surface. Earth's protection is layered: magnetic field, atmosphere, ozone, gravity chemistry, distance from the Sun, planetary size. No single shield does everything. That is why the best image is not one wall protecting one fragile world. It is a series of filters, each doing a different job. The magnetic field deals mostly with charged particles and space weather. The atmosphere absorbs and scatters radiation, slows incoming particles, burns up small meteoroids, and makes pressure and climate possible. The ozone layer absorbs much ultraviolet radiation. Gravity holds the atmosphere. The planet's interior helps maintain the magnetic field and releases gases over geological time. Remove the magnetic field, and the system still has defenses. But one major defense is gone. Now the upper atmosphere is hit more directly by the Sun's particle environment. During intense solar storms, more energy enters. More atmospheric particles may be energized enough to escape. Satellite electronics face more radiation stress. Astronauts beyond low Earth orbit face greater hazards. Communication systems must deal with a harsher ionosphere. The planet's polar beauty may become a broader warning glow. Imagine a solar storm arriving at a weakened Earth. In space, the solar wind front reaches the planet. With a strong magnetic field, the particles are deflected and shaped around the magnetosphere. With a weak field, the interaction moves closer. The upper atmosphere glows more widely. Satellites in orbit pass through turbulent particle regions. Radio signals bend and scatter through disturbed layers. Electrical systems on Earth may face stronger geomagnetic effects depending on the storm geometry. The ground remains familiar. That is part of the danger. Most important damage may be above the weather. Inside the systems that modern life quietly depends on: GPS timing, satellite internet weather forecasting, Earth observation, aviation communication, spacecraft navigation, military and civilian communication networks, power grid monitoring, scientific satellites. The magnetic field is not only a planetary science topic, it is part of the hidden infrastructure of modern civilization. But Earth had a magnetic field long before humans needed satellites. So the older question is biological. Would life survive? At the surface, the atmosphere still protects life from many immediate radiation hazards. Underground life, ocean life, and many surface ecosystems would not vanish instantly because the magnetic field weakened. Life is resilient across environments, and Earth's atmosphere is a powerful shield. The immediate biological consequences would likely be much less dramatic than the technological consequences. But over long periods, increased radiation at high altitudes and in near-space environments could matter. Changes in atmospheric chemistry could matter. Increased atmospheric escape could matter over deep time. More intense exposure during solar storms could matter for organisms near the upper atmosphere or in aviation and space contexts. The key phrase is not instant extinction. It is long-term vulnerability. A planet can remain alive while becoming more exposed. A civilization can remain standing while its orbital systems become more fragile. A sky can remain blue while the boundary above it becomes more dangerous. Now look again at auroras. In a strong storm, auroras can move far from the poles. People at lower latitudes can see curtains of light. In a weakened field scenario, the geography of auroral activity could change because charged particles would reach different regions more easily. The night sky might become more spectacular more often in more places. But a brighter aurora is not just beauty. It is energy entering the atmosphere. That energy can disturb the ionosphere, the electrically active upper atmospheric region that affects radio communication and satellite signals. It can heat upper layers, causing them to expand. For satellites in low Earth orbit, an expanded atmosphere means more drag. More drag means orbital changes. During severe events, satellites may need corrections, and objects can become harder to track. This has already mattered even with today's magnetic field. A weaker field would make the margin smaller. The invisible shield buys time, distance, and predictability. Now imagine the magnetic field fading over thousands of years. At first, humans might notice more space weather disruptions. Satellite design would change. Space agencies and companies would add more shielding, more redundancy, more forecasting, more safe mode protocols. Astronaut missions would need stricter radiation planning. Aviation routes might adjust more often during storms. Power infrastructure would need better protection against induced currents. The problem becomes expensive before it becomes existential. Then imagine the field gone for millions of years. Atmospheric escape becomes a deeper concern. The solar wind has more direct access to the upper atmosphere. Some particles are lost to space. The rate depends on solar activity, atmospheric chemistry, gravity, and many other factors. Earth would not become Mars quickly, but its atmosphere would be under a different kind of pressure. The Sunday itself changes over time. As stars age, their brightness changes. The young Sunday was more magnetically active, and early planets faced stronger space weather. In the far future, the Sunday's increasing luminosity will affect Earth's habitability regardless of the magnetic field. So the magnetic field is part of a larger planetary survival story, not the only chapter. Earth's atmosphere is not simply sitting there. It is being produced, altered, lost, recycled, and chemically transformed over time. Volcanism releases gases. Weathering removes carbon dioxide. Biology changes oxygen and methane. The ocean absorbs and exchanges gases. Escape to space removes some particles. The magnetic field influences part of the lost environment, especially charged particle interactions. Planetary habitability is a balance, not a lock. The magnetic field helps keep that balance more favorable. Now consider what losing it would not do. It would not instantly pull the atmosphere away like a tablecloth. Gravity does most of the holding. It would not make compasses simply spin forever in chaos as the main disaster. Compasses would become unreliable if the field weakened or became complex, but compass failure is small compared with the space weather story. It would not turn Earth into Mars overnight. It would not make sunlight suddenly become lethal at sea level in one day. The real version is slower, deeper, and in some ways more frightening because it is not a single event, it is a change in exposure. A planet with a strong magnetic field is not isolated from space, but it has a powerful way to shape that interaction. A planet without one has fewer options. The solar wind can reach closer, storms can couple more directly. The upper atmosphere becomes more vulnerable. Technology in orbit becomes harder to protect. The shield is not a wall. It is a negotiation. Every second, the Sunday pushes outward. Earth's magnetic field pushes back. Where they meet, a boundary forms. That boundary moves closer and farther depending on solar wind pressure. During calm conditions, it holds. During storms, it shakes. When the field is stronger, the negotiation gives Earth more room. When weaker, the Sunday gets closer. Now return to the opening image. Solar particles slam into blue magnetic lines. The lines bend and flow around Earth. Auroras ripple at the poles. Satellites cross through charged regions. Beneath all of it, oceans turn, clouds form, forests breathe, cities glow, and almost no one feels the magnetic shield doing its work. That invisibility is why the magnetic field is easy to underestimate. We notice atmosphere because we breathe it. We notice gravity because we feel weight. We notice sunlight because it warms the skin. We do not notice the magnetosphere unless instruments reveal it. Satellites suffer from it, or auroras paint the sky. But Earth's magnetic field is one of the great planetary systems that makes the surface feel separate from space. Without it, space does not hit the ground all at once. It moves closer layer by layer, closer to satellites, closer to the upper atmosphere, closer to the systems that guide aircraft, forecast weather, connect continents, and watch storms from orbit, closer over thousands and millions of years to the atmospheric edge that helps keep Earth stable. The final image is not Earth dying in a flash. It is Earth still blue, still clouded, still alive, but with its glowing field lines faded almost to nothing. Solar particles stream closer than before. Auroras spread in strange wide rings. Satellites flicker through a rougher sky far above the oceans. The place where Earth used to push back against space has moved inward. The shield was invisible, only when it weakens. Do we see how much of the planet was protected by something we never felt?